The first is Bettina Lotsch. Professor Lotsch is the director of the nanochemistry department at the Max Planck Institute for Solid-State Research in Stuttgart, Germany. And she is also honorary professor at the University of Munich and the University of Stuttgart. Professor Lotsch's research leads the field of new material synthesis by combining tools from molecular, solid-state, and nanochemistry fields. Her research has been recognized by numerous awards and honors. I will just give two of them as an example. She is a fellow of the Royal Society of Chemistry, and most recently she has won the Leibniz Prize of the German Science Foundation. So, please, Bettina.
Yeah, thank you very much, Bilge, and good afternoon, everyone. Thanks to the organizers for putting together such a wonderful program, and of course for the possibility to speak here today. So what I would like today to do today is tell you how we can control ions with light. So as you can imagine, this is in the first place a materials challenge. And so I would like to go back and talk a bit more about the materials in which we discovered so-called optoionic effects, and then show you how we can put these effects to use for light storage applications, and also how we can use them to derive design concepts for other types of optoionic systems. Now, the materials I'd like to talk about are carbon nitrides. Carbon nitrides belong to, let's say, the oldest synthetic class of materials, or at least polymers. And already the godfathers of chemistry, Justus von Liebig, Berzelius, Wöhler, they all were interested and fascinated by this class of materials. Now, carbon nitrides even made it into a Vanity Fair attraction, known as Pharaoh serpent. So here basically you can see the burning of mercury thiocyanate in air. And this yellow mass that comes out of it, the reaction product, is called melon, or has been called melon by Justus von Liebig. And this actually, he states here, so this name melon, he had given to this class of material, this material, for no obvious reason. So it's a kind of random name and a bit of a weird nomenclature. And actually, you'll find similar names like melam and melem in this class of materials. Now, Justus von Liebig also realized that these materials have something in common with animal compounds, as he called them, so animal excretions, because you can make polymeric carbon nitrides, and also his melon, by starting from very simple molecular carbon nitride precursors, like cyanamide, like urea, like dicyandiamide. So they are all sort of related to, these animal excretes, like urea and uric acid. So carbon nitrides are typically made in a solid gas reaction. So basically, these molecular compounds are condensed in a solid gas reaction, and then ultimately they form a one-dimensional polymer that is called Liebig's melon, as I mentioned before. Now, nowadays, you would actually know this material melon under a different name, namely carbon nitride, simply graphitic carbon nitride. This is what typically people understand, when they when they have this Liebig's melon in their hand. So this is not actually a two-dimensional material, graphitic carbon nitride, but it's a one-dimensional polymer. However, we can also make two-dimensional carbon nitrides, as you see here, when we switch from a solid gas reaction to an ionothermal reaction. And what we end up seeing then are these sort of polytriazine imides or polyheptazine imides that are shown over here. So these are true two-dimensional carbon nitrides. And for much of my talk, I'll actually stay with this two-dimensional carbon nitride over here, which is called polyheptazine imide. So in a nutshell, let me explain to you the structure and nature of this material. So polyheptazine imide is a two-dimensional carbon nitride that is based on these heptazine units, but it is also an ionic carbon nitride, so it has hydrated potassium ions in the pores. It is fairly crystalline, and the layers are stacked on top of each other so that one-dimensional sort of pore channels arise from this. Now, we got interested in this class of material a long time ago, also for its interesting photocatalytic properties. And what is really remarkable about this material is when we compare it and its optical properties with the prototypical carbon nitride, melon, or graphitic carbon nitride, we see that the band gap is essentially identical, 2.7 eV, but the photocatalytic properties are significantly better. So hydrogen evolution is much more, or the material is much more active for hydrogen evolution by about a factor of 20 compared to the typical graphitic carbon nitride. So this is striking, and we were wondering why this is. And so one of the clues why this sort of high activity is observed lies in the optoelectronic properties of this material. So in a nutshell, in the transient absorption spectrum, we see that when we irradiate PHI in the presence of a sacrificial electron donor, and this is probing, so this is exciting at 355 and probing in the blue region of the spectrum, then we see a very long-lived component coming up. This is not the case for melon, and this long-lived component is consistent with trapped electrons. We also see this in the EPR spectra, and we even see this visually by eye. So when we photoreduce the material in the presence of an electron donor, then PHI turns blue. Now, this is only half of the story. These are the optoelectronic properties, but remember that this is actually an ionic compound. So the carbon nitride backbone is charge compensated by potassium ions in the pores. So what about the potassium ions? So in fact, this material, sorry for that, this material and also the other alkali metal derivatives, they are ionic conductors. So we find ionic conductivities in the range of 10 to the minus 5 Siemens per centimeter, depending and increasing with relative humidity. So these materials are also ionic conductors, and what is quite remarkable is that there is a correlation between the ionic conductivity and the hydrogen evolution activity of these materials. And this is also seen in the photoluminescence lifetimes. So we see the highest photoluminescence lifetimes and highest hydrogen evolution activities for the sodium species. So at this point in time, we can only say that there is a correlation between these properties, the ionic properties and the hydrogen evolution conductivity. We cannot say yet that there's also a causation between them. But we believe that there's actually a causal relationship as well, as I'll show you, on the next slides. So at this point, let us put together the pieces of the puzzles and what we've learned, and look at what we've learned so far. So basically, this material, so this is kind of the mechanism that we invoke. This material, when we illuminate it, forms electron-hole pairs. The holes get extracted rapidly due to the high hole transfer reactivity of PHI. So in other words, this material is highly, it's a very good oxidant, so we can easily extract the holes by the sacrificial electron donor, as you can see here. At the same time, the electrons stay on the material and get trapped. But not only that, so we assume that there is a screening of the light-induced electrons by the mobile cations in solution. And this actually gives us the possibility to separate the light-induced oxidation reaction from the reduction reaction. So basically, we are separating here the two half reactions of photocatalysis. And when you look at it, this is essentially an optoionic process because we're coupling light to the ionic sublattice of the material indirectly via the electronic charge carriers. Now, is this fundamentally new? Are such optoionic processes unheard of? And the answer is, of course, no, they aren't. So a couple of years ago, in fact, decades ago, Tribuch suggested that in two-dimensional p-type transition metal dichalcogenides and also agarodides and other sulfides, a process called photointercalation is at play. So let me just walk you quickly through this photointercalation concept. So basically, the material is illuminated, electron hole pairs are formed, the light-induced electrons, they provide the driving force in here over here in the quasi-Fermi level to attract cations from solution into the bulk of the material. And at the same time, the light-induced holes are extracted via the electrode. So at the same time, the sort of electrons provide, when they provide the driving force to intercalate the cations from solution, the electrochemical potential of the system increases. And so effectively, what we do here is we store solar energy. Now, this has been proposed by Tribuc for photoelectrochemical systems. Now we can do the same thing with, in a photocatalytic setting by switching from p-type semiconductors to n-type semiconductors. So here essentially what happens after light excitation is we extract the holes, the minority charge carriers, via the solution by providing a sacrificial electron donor, whereas the electrons stay on the materials, and at the same time sodium ions from solution intercalate into the system. And I should mention that this has been shown for molybdenum trioxide, so an n-type oxide, and this is actually a very nice example of a photointercalation system that has presented a couple of years ago by the group of Rose Amel. So when we look back at what happens in the carbon nitride, PHI, then actually, in essence, this is a very similar process. A kind of photointercalation, we have a two-dimensional system. We are intercalating ions from solution into the one-dimensional channel of the carbon nitride, and the electrons sort of remain on the heptazine units and are screened by photointercalated cations from solution. So this is a, if you will, a photointercalation process. Now, what we see in all these examples that I've shown you so far is that there is a detailed balance between the electronic charge carriers and the cations from solution. So basically, there's a kind of a detailed balance between electronic charge carriers and ionic species. And this process is actually a process, when you look back at the literature, that has been described for many other systems, in fact, especially oxides. For example, titanium dioxide or also strontium dioxide, where light-induced oxygen incorporation or excorporation is charge compensated by transition metal redox. So this leads to coupled changes in ionic and electronic conductivity in the system. Actually, another very recent example has been presented by my colleague Joachim Meyer, and this is the prototypical hybrid perovskite MAPI. So here, light excitation leads to the oxidation of iodide, and iodide then displaces into an interstitial forming an H center, and that ramps up the ionic conductivity, vacancy-mediated ionic conductivity by orders of magnitude. So these are all optoionic processes. And the good thing about these processes is that they give us a handle to control ions with light and to effectively directly store solar energy. So let's see what we can do with this property of certain materials to directly store light. So I'd like to walk you quickly through a couple of applications that we have come up with, starting with dark photocatalysis, and then direct solar batteries, photomemristive sensing, and solar battery swimming. So bear with me. I'll start with dark photocatalysis. So here, the idea is to separate the light-dependent and light-independent steps of photocatalysis. And this is a bit reminiscent of what Mother Nature does in natural photosynthesis. So the idea is to charge up, to photocharge the system by light, and then turn off the light, and add a co-catalyst in the dark. And so if this works, then we can produce hydrogen with a time delay in the dark. And in fact, as you can see here, this is happening. So we turn off the light, and then we can wait a couple of hours, even up to 10, 12 hours, and still produce hydrogen in the dark simply by harvesting the trapped electrons on the material. Now, this is, as I mentioned, reminiscent of natural photosynthesis. So here in photosystem 1, the light-induced or photoexcited electrons are shuttled across a complex, let's say, electron transfer chain, and eventually they are, fixated in the form of NADPH. And then, this sort of energy carrier is then used for CO2 fixation in the dark, in the Kelvin-Benson cycle. So in other words, Mother Nature has evolved two energy storage systems. One, let's say, rather short-term storage system where energy is stored in NADPH and ATP, and these are high-energy molecules that are shuttled around in the cell and sort of available on demand very quickly. And then we have another more long-term energy storage system, which is related to the Kelvin-Benson cycle, where CO2 is fixated as carbohydrates that are stored sort of more permanently. And that would correspond to the hydrogen that we can produce also via dark photocatalysis. So we believe that what we have created artificially with PHI is actually very reminiscent of this sort of short-term energy storage system. And so a question would be, where is such a short-term storage system actually of use? So, what can we do with it? And so the answer is that we can use such a storage system everywhere where sort of light energy needs to be available also in the phases where, let's say, the sun doesn't shine. So that can be, for example, during cloud overcast, or when we like to shift the availability of solar irradiation into the dark phase, into the evening after sunset. And this is the so-called duck curve that shows the power load on the grid in sun-rich regions, like here, for example, where the peak demand is actually after sunset, and so the load on the grid is highest in the evening when the sun doesn't shine. So it would be nice to have a kind of solar buffer system that keeps, let's say, solar energy available in the dark phase, right? So, so we do have a number of, let's say, intermediate to long-term storage options. We can couple PV, for example, with battery storage or with pumped hydroelectric. But what we have here with the dark photocatalysis is a kind of short-term buffer system that provides persistent energy production in the dark phases in the near term. And so here we can use dark photocatalysis. But another concept would be to sort of store the charges, and rather than transforming them into a fuel like hydrogen, keeping them and then extracting them as electrical energy. And that would actually give us a solar battery. Now, a solar battery is essentially a battery that we can charge up with light. And this concept is very much related to what I've just shown you for dark photocatalysis, with the difference being that now we need to separate the charges and reversibly store them in an anode and a cathode. And so this actually becomes tricky, especially if we want to do this in a highly integrated fashion. And let me mention that, again, PHI is able to do this because it combines the function of a solar cell, so we can create a photocurrent. But we can also, if we scan negative of the open circuit potential, we can store charges on the material. So essentially, PHI gives us the possibility to create a photoanode that can both absorb light and store charge. Now, I mentioned the integration problem. So if you want to reversibly store electrons and holes and make sure that they don't recombine, we need to be clever about how to sort of integrate the system and prevent recombination. That is a challenge. And when you think of a solar battery, you can just think about a two-device type of system. So a solar cell that is coupled to a battery. So this is kind of a simple way of thinking of a solar battery. A couple of years ago, actually, about 30 years ago, Kayan and Holtz suggested a sort of greater level of integration. And they integrated a dedicated photoanode with a storage anode and cathode. So that saves us electronics, it saves us converters, it saves us charge controllers, but of course we need to make sure that the energy levels in this system are aligned. Now, this is not the end of the story of integration. We can go one step further. And what you see here is basically a two-electrode system where we have one heterojunction type electrode that is composed of a layer that absorbs the light and another layer that stores the charge. So this is even one step further towards integration. Now, what we have done with PHI is actually going yet another step further, because here we have one single material that absorbs light and stores charge. So this is the most highly integrated version of a solar battery. You can imagine this is the photoanode based on PHI. This is a multifunctional separator that is there to prevent charge carrier recombination and to shuttle the holes into the storage electrode P.PSS. So here you can see that is a highly compact design of our first optoionic solar battery. Now, to appreciate the function of the solar battery, let me mention again that we can run the system as a solar cell, actually a quite lousy solar cell. We can also run it as a battery, a dark battery. But the solar battery function is what we are actually targeting, and here we have two operation modes. So we can either purely charge the system by light, or we can combine light and electric charging. And this light and electric charging is actually the preferred operation mode, because here the capacity utilization is maximum because we're creating charges near the separator and near the electrode. And so we're just using the volume of PHI optimally. Now, what I didn't mention, and what is actually a quite interesting sort of property of this device, is that we can not only photocharge the battery and then discharge it in the dark, but we can actually, and this is seen in these GDC curves here, we can also illuminate it while we're discharging the solar battery electrically. And that gives us additional capacity. So in this Ragone plot, you see that the system is most efficient, as you can imagine, when we run it or illuminate it at, in the near UV. You can also see, or let me just show you, you can also see that the energy and power densities, are moderate, so there's certainly a lot of room for improvement. But this arrow here shows you that, in the limit of discharging the battery very slowly and illuminating it while discharging it, we can actually gain quite substantial charge extraction. Okay, so with this, let me switch over and show you what else we can do with photocharging materials. And here I'll be very quick. So we can also use photocharging materials for sensing. Now we're kind of coming back to the concept of dark photocatalysis, but now we're replacing the sacrificial electron donor with an analyte of interest. And so we're using the charge accumulation on the system as a readout for the concentration of the analyte in solution. So this is not just a typical photoelectrochemical sensor where we are creating a transient photocurrent in the presence of an analyte under illumination, but the system is special because we're creating sort of a persistent photopotential when we illuminate the system. So in other words, we are writing concentration information onto the sensor, and then we can read it out at a later point in time. So this gives this sensor a memory function. And it also, of course, this sort of charge accumulation affects the resistive properties of the material, and so we call it a photomemristive sensor. Now, the system is highly integrated. It is a receptor, a transducer, and an amplifier at the same time. And the amplifier function simply comes from the fact that by choosing the illumination time and also the illumination intensity, we can adjust the concentration ranges that the sensor is sensitive to. Now, in a nutshell, we have different readout modes that we can invoke. So here you see one of the readouts would be potentiometric, so via measuring the photopotential upon charge accumulation. Another one is impedimetric, so via the AC resistance. And the third one is by simply extracting the charges that we're accumulating and sort of counting the charges in a coulometric mode. So these are all readout modes that require a thin film, which is actually not so easy to make in the system. But we can also use particles in solution, and we can simply read out the concentration, and I should mention that we have done this for glucose as an analyte. We can read out the concentration colorimetrically, so simply by looking at the color change of the material as a function of analyte, and fluorometrically by looking at the photoluminescence quenching. Okay, coming to the final application of these photocharging materials, well, this is actually an application that is sort of, moving away a bit from, solar fuels and energy production. And this is actually an application from the field of active matter and autonomous systems. So in the field of active matter, it has been shown not too long ago that one can use photocatalytic reactions to drive micron-scale particles. And the way this works is that if you have an asymmetric surface reaction, so for example in desymmetrized Janus-type particles, then a concentration gradient builds up across the surface, and this acts as a kind of chemical pressure to drive a particle forward. And we were interested in seeing if our PHI actually can do this, but we're even more interested in seeing if we can photocharge the PHI in the light and then sort of turn off the light and see if the particle keeps swimming in the dark. So this was the idea. So introducing a new mode of propulsion, essentially, that works through photocharging. And so basically, this is what you can see here. So now the particle is in the dark. Now we turn on the light, and you see it kept sort of swimming, or sort of we turn off the light, and it keeps swimming in the dark. So this was a bit quick. The video will replay, so maybe you can catch it the second time. So basically, this is a photocharging process. We turn off the light, and the particle keeps swimming. Now, what is peculiar about the system is that it combines a lot of really interesting properties. So for example, it shows phototaxis, which means it swims towards the light. It also is very tolerant to high salinity media, which means that these particles can swim where other particles are dead on arrival, because typically high salinity media, complex biological media, would not sort of support movement of these particles. But here this is different, and these particles swim in 1 molar NaCl solutions, and very complex, also diluted blood and other complex biological media. Now, this together with the fact that these systems are highly biocompatible makes them very interesting, for example, for drug delivery and theranostic applications. I won't go into detail any further today. Maybe this is something for next time. Now, at this point, let me sort of zoom out a bit. We have learned that we can use photocharging for a number of applications, from solar batteries all the way to dark photocatalysis or sensing. But in order, to really make use of this property, we need to understand the optoionic mechanisms, and understanding optoionic mechanisms will then help us to rationally design optoionic materials, because after all, we don't just want to play around with carbon nitrides. So Well, I guess we're only at the very beginning of understanding what kind of optoionic mechanisms exist. And what you see here is a very rough sketch of what we know. So basically, I'm distinguishing between two types of broad mechanisms, and their interfaces are somewhat blurred. One is charge trapping, and the other one are more long-ranged field effects. So in a nutshell, charge trapping includes defect formation and photointercalation processes, and these are essentially the processes I mentioned in the beginning, for example, in MAPI, or also light-induced oxygen non-stoichiometry that is charge compensated by transition metal redox in systems like titanium dioxide or strontium titanate. Photointercalation is a somewhat, let's say, less local property, and it can basically range from purely intercalative all the way to predominantly pseudocapacitive, which will affect the charge trapping properties in these systems. But all of these processes here on the left-hand side are essentially connected to short-range stoichiometry changes, and they are persistent in nature. And this is what we want for charge trapping, right? We want to trap charges for, an extended period of time. They are also predominantly Faradaic in nature, so there are redox processes involved. On the other hand, field effects are more long-ranged effects, and they typically operate in space charge regions. So basically here, charge accumulation in space charge regions can, for example, change the grain boundary potential barrier in systems like Syria and then increase ionic conductivity. This has been shown beautifully in a work by Harry Tuller and Jennifer Rupp recently. We can also use charge accumulation in space charge layers to sort of induce ion migration in ion pumping type systems for photoelectrical energy conversion. These systems are more long-ranged, and they are typically transient. So when we turn off the light, then the system goes back into its initial state, and they are predominantly capacitive in nature. So since we are mainly interested in more permanent charge trapping effects for solar batteries, for example, let me come back to photointercalation and show you two more examples quickly in the remaining couple of minutes. Examples that are distinct from carbon nitrides, both chemically and structurally. So the first example is a layer transition metal oxide, a niobium tungstate, where the niobium layers here are sandwiched by tungsten oxide layers. So this is a photochromic material, and photochromism is actually a very good indicator for optoionic properties. So when we irradiate the system, in the presence of an electron donor, in this case methanol, we see the system turns blue, a property that is very similar to carbon nitrides. And when we look at the photopotential, we see that the photopotential goes negative to round about minus 0.8, and then when we turn off the light, it actually stays there for about 20 hours or more. So there's a quite, let's say, pronounced charge trapping ability in the system. Now, in a nutshell, our calculation suggests that the mechanism is polaronic in nature. So essentially, the light-induced electrons localize at distorted tungsten sites that are next to oxygen vacancies. There is a possibility that also the niobium sites act as charge storage reservoirs, but we haven't yet been able to really access this capacity that is associated with the niobium sites. So basically here, charge trapping occurs by the formation of small polarons. Let me also mention that what I've shown here in terms of charge trapping is a signature property of a solar battery. So we want, charge trapping across, for several hours. But in this system, we could also show that that this material can evolve hydrogen in the dark. So it's basically able to combine photocharging and dark photocatalysis, similar to carbon nitrides. And what we're currently working on is a so-called solar battleizer. So basically, we're developing a system that we can photocharge, and once it is fully charged, it can evolve hydrogen. So basically, we have two storage options, one that is a bit more short-term and one that is a bit more long-term. Okay, so the final example is chemically, again, very different. So this is a two-dimensional covalent organic framework that is based on NDI units. So this is naphthalene diimide, and naphthalene diimide is a chromophore that is well known for its electron accepting properties and electron sort of, storage properties. So we were curious to see if this material could be photocharged, and indeed it can. So here in the UV-vis spectra, we clearly see the signature of a 1 electron reduced NDI unit when we illuminate the system in the presence of an electron donor, here 4-MbA, so 4-methyl alcohol, and this is consistent with the EPR measurement. So here an NDI anion radical forms. What is interesting and also not too unexpected is that we see an increase of the conductivity of the system by 4 orders of magnitude. So apparently here, on photoreduction, we're moving from, let's say, a redox hopping type process that goes from isolated, or is between isolated NDI minus units to a kind of band-like charge transport. But this is something that we're looking into at the moment in a bit more detail. Now, the charge storage properties of the system are also quite remarkable. So we can store the electrons for more than 12 hours. We have a high capacity retention after 12 hours storing in the dark of more than 70%. Also, the cycling stability is very high. And when we look at the combined capacity, also energy density, power density, these are definitely and significantly increased over what we have seen in carbon nitrides and transition metal oxides. Now, this makes this material a very interesting system for solar batteries and also dark photocatalysis. And so we were wondering, what is actually the precise role of the cations in the system? And I have to say, so this is work in progress. Let me just mention in a nutshell that we see when we change the ion type, the ion concentration, and also the pH, that there's essentially no significant effect whatsoever on the charge storage properties, neither on the capacity nor on the duration. In fact, if we add ions, the charge storage capacity is rather slightly decreases than increases. So this is actually quite puzzling. The only factor that really plays a significant role is the concentration of the reducing agent, or of the of 4-MbA. So the concentration clearly scales, or the capacity scales with the concentration of 4-MbA, and also the solvent is quite important. So we see the highest charge storage capacity clearly in water. So that leaves us with the question: what is actually the role of ions in the system? How is sort of charge compensation achieved? If we take the necessity for charge compensation as a given, and I think it's reasonable to do this, so when we accumulate electrons, we also need to compensate the charge, then we can sort of invoke a combination of 3 different factors that help us to stabilize the electronic charge. One factor certainly is local solvent screening and the dielectric properties of the solvent. So, the higher the dielectric constant, the better hydrogen bonding, the better this negative charge on the system can be stabilized. We also assume that electrons can be delocalized into or across the NDI units. And this is actually seen very nicely by the band diagram. So here, when we look between the gamma and the A direction, we see the highest dispersion, and this is actually along the stacking direction. So that tells us that the charge on the NDI unit can actually be delocalized across the stack. And we also assume, finally, that there's remote charge compensation by the ions in solution. So there are, of course, ions in solution, and there will also be ions produced, for example, by oxidation of the sacrificial electron donor. And so these factors all play together to stabilize the negative charge on the system. Okay, with this, I'm at the end of my talk. I hope I have shown you that the properties sort of photocharging and optoionics is intriguing to come up with new hybrid energy concepts, solar batteries, dark photocatalysis. But there's actually also a lot of potential, for example, for light-driven synaptic memory devices and sensing. But in order to push this forward, we need to understand optoionic mechanisms better. And we also need to know how to really rationally design optoionic materials. So with this, I'd like to thank my fantastic team, who really, without whom I wouldn't be here. They did all the work. It's fantastic to work with them. And thanks also to our collaborators from theory and beyond. Thanks to the funders, and thank you for your kind attention. Thank you.
So much for this fascinating, very creative research that you shared with us. Now we are open for questions.
Bettina, very nice talk, very interesting talk. I was just wondering, when you're doing this solar batteries, what's the time scale of charge separation that you're talking of?
So charge separation is actually very rapid. It has to be because recombination is fast on the nanosecond time scale. So simply judging from the natural charge recombination that we see in the system, it is rapid, but this is exactly the reason why we add the separator, F8BT, which sort of prevents the naturally occurring charge separation. Now, what I didn't mention, but what you might have guessed actually from the architecture, this charge separator does not only separate the electronic charges, but it also needs to be transparent for ions. And this is actually a property that is kind of special to this specific material and makes the whole setup very sort of delicate. Yeah.
Very interesting talk. Thank you.
Very good. Any other questions? Yeah, there is one in the back there.
Nice talk, thank you. You made the analogy a couple of times between your material, your carbon nitride material, and oxides for charge trapping. And in the oxides, of course, it's vacancies that are absolutely involved, vacancies. I still can't understand what is the origin of charge trapping in your nitride materials. I mean, do you have you have crystals of these things? Do you have defects actually in there?
So we do have defects in these systems, but they are most certainly not responsible for the charge trapping. So the idea basically is, and I think it really helps to think of the system as a photointercalation system. So the heptazine units are the sites where the electrons are trapped. And this works so well because heptazine units are very electron poor. So they can receive electrons and delocalize them, not just across this one heptazine unit, but they can actually, I mean, there's most likely a delocalization across about 2 heptazine units. This is what we know from EPR. Now, at the same time, the charge balance occurs through the cations that intercalate into the system. So basically, charge trapping is a kind of photointercalation process, as we've seen, or as we see actually in several oxides. I'm not sure if that sort of answers the question, but we can also discuss afterwards. Yeah.
So I have a related question. So among these different phenomena, light-induced charge trapping, light-induced intercalation, light-induced extended effects like interface field effects that you interfere with, in your material or in any of these materials, do you think it's only one of these mechanisms acting, or a combination of field effect and a more local phenomenon that could be taking place? And how do you disentangle them?
Yeah, that is a very good question. So we believe, that this is something that we will be looking at soon. But we believe that there's actually a bit of a let's say combination of effects. So photointercalation on the one hand, but also, I mean, when you look at you know, when you look at the system and also look at the morphology of these systems, so we really can't exclude field effects or long-range field effects to be at play. And in fact, I think they are very necessary actually in the system.
Is it possible to control the size of your particles to
Yeah,
get
I mean,
to their relative interface effect?
Yeah, exactly. This is kind of something we're looking at right now. We do see, you know, when we do a kinetic analysis of the intercalation process, we do see that it is mostly pseudocapacitive, but this will certainly change with the size of the particles. You know, it's simply not so easy to do this, to change the particle sizes and morphologies in these systems. But this is exactly what one would need to do to really disentangle these different effects. And yeah, I can simply say there's a lot that we do not yet understand, and that you know, we need to look at.
Very creative direction.
Thank you.
Great. So thank you so much, Bettina, for this
Thank you.
wonderful talk.